Let's create a new environment and go along the agent step by step to see how it's learning to navigate. We will start by adding new states to the environment. Just click on the graph area to create a new state. Let's say two more states, S1 and S2. Then we create reward connections between these states. From SX to S1, S1 to SX, agent can move from S1 to S2, agent gets rewarded moving from S2 to S1, and from SX to S2. Then we give them a little arrangement. Now try to reach SX from S1 using rewards. I mean, follow the path to SX which gives maximum reward. Since agent gets rewarded for going to S2 from S1 as well, there is no guarantee that it will always reach the destination SX from S1. If we use only rewards information, 50% of the times agent will be moving between S1 and S2. It's clear that rewards cannot be used to navigate. Before moving on to the details, let's remember that the agent is blindfolded. At any given point in time, it has only three pieces of information, which are number one, the current state, number two, doable actions in the current state, number three, reward, which is received only after taking an action. Using only this information, what will you do to find the best way to destination? Pause the video, take a moment and think about it. Here is what the agent does. It will try going to different states randomly, take action, receive reward, and update the quality of action. Over time, this seemingly random walk results in emergence of a perfect solution to the problem. If you haven't checked the first video, then please have a look to appreciate how this simple sequence of operations finds befitting solutions to different problems. To revise our understanding, let's read the environment graph and corresponding rewards and Q table together. Remember, each cell in the rewards table represents the reward for taking an allowable action in a given state. The column name is current state. The row names are the future state that we can go from current state. For instance, when in state 2, agent can take three actions. Let's name them A2X, A21, A22. The reward for A21 is 1. As you can notice in the graph, a reward is represented by a directed edge between two states. So this is A21 action. Similarly, the Q table stores the quality of action for all possible actions doable in each state. Each cell of Q table represents quality of corresponding action. The column name is current state and the row name is the future state that we can go from current state by taking these actions. Before the learning starts, the quality of all actions is initialized to be 0. For example, the quality of action A21 shown in the graph as label of directed edge between these two states. Please note that the graph shows quality of only actions with rewards. For example, the Q value for action A2X is not present in the graph because A2X has 0 reward. So revising again, in each state, agent can take an action that will move agent to another state. In each state, there are as many doable actions as there are the states. Since agent receives a reward only after taking an action, therefore, during learning, an agent can take an action with zero reward. For example, it can choose to go to from S2 to SX. The action A to X, even though it's not shown in the graph because reward is zero, however, agent can choose to take that action because agent is blindfolded. Now let's discuss the mechanics, how agent will interact with environment. It will take essentially three steps in a sequence, repeatedly enough number of times. Step number one, it will randomly pick a state and decide whether to explore or exploit the available actions. Number two, it will take an action to receive a reward if there is one. Number three, the agent will update the quality of action just took using the reward and past experience. Now, if you look at the left hand side of the tutorial screen, there is a button titled Step. Clicking the Step button will show what the agent is doing at a given point in time. The details of agent's actions appear in a text box on top left corner of the graph. Let's click. In this step, the agent randomly selected S2 to be the current state, and then agent decided to explore its options for available actions, and it chose A21 to be the action which took it from S2 to S1. After moving to S1, agent has to update the quality of action A21. How does agent updates this quality is calculated here. Agent first calculates an important number, temporal difference. Let's call it TD. The reward for A21 action is 1, and the quality of A21 was 0 before agent took this action. So the current state, if you notice, is colored as light green, and the future state is colored as dark green. So agent does this calculation of taking the difference between maximum achievable quality from S1 discounted by a factor, let's call it discount factor, and quality of action that agent just took. For now, the TD value is 1. Temporal difference, or TD, represents the change in quality of an action based on discounted quality of future and reward achieved by taking this action. The logic is very simple. If an action A takes agent to a future state with high quality actions, then the quality of A must be increased because it is leading to a better state. Otherwise, it should be decreased. So based on this logic, we calculate temporal difference and use this value to update the quality of action A21. It's like when you decide to go to a restaurant and find high quality food with good price, and having that meal makes you do high quality activities in future, then you want to go there again. In the same fashion, agent calculates the temporal difference as reward plus discounted maximum quality action possible in future state minus current value of action just taken by the agent. You may ask why maximum achievable quality of future state is discounted. The answer is in the going to same restaurant example. Think about it. Even though this time you experienced very good food, but the menu, chef, or other factors may change over time. there is no guarantee that next time the food and price will be the same. Therefore, you don't want to give full credit to just one time experience. Instead, you would like to discount the value of your going to same restaurant action by a small factor. That factor is discount factor. Secondly, if we pay attention, the maximum quality action possible in future state is depending on the future state, which is calculated from the future state. You can say that the future state assumes the quality of best possible actions of all future states. Therefore, it is only wise not to let a farthest future state overshadow the quality of an action that the agent has just took. It's like you won't assign high value to going to same restaurant action because it can enable you to take the train on time next week. There may be an association, but it's not prudent to give full credit to it. For the same reason, the agent is discounting maximum quality action possible in future state by discount factor. After calculating TD, what next? Now the agent updates the quality of selected action, which is A to 1 here, by scaling the TD to a learning rate factor. Another scaling factor again. Now, why do we need this? Well, remember the agent is blindfolded. It's quite possible that the agent may learn a wrong step during numerous random interactions with the environment. Which means at some point the agent may believe that going from S2 to SX is a high quality action, which actually isn't. The learning rate scaling takes care of this. If the rate is high, the agent may get misled by temporary spikes in the quality values. If the rate is very low, the agent will take longer time to learn the optimal solution to the problem. Let's keep the agent busy taking these steps for large number of iterations. Press Enter key and keep it pressed. You can see that the Q values are being updated and agent is learning and updating them, taking different positions, different states, and going to the next future states. And after a large number of time, we can stop and see what agent has learned. So after 1000 iterations, let's test agent is taking which path to go to SX from, let's say, S1. So this is what we wanted it to learn. And from S2, it is taking the correct path. And when we click SX, so agent is choosing to stay in the same state. And if we look at the Q table, we can see the corresponding Q values for taking an action in each given state are also updated. So far, so good. If you think this problem is too simple, then please check the first video or try creating your own scenarios. You can access this tutorial online on this URL, spimlab.com/learn/RL. So far, we have discussed the nuts and bolts of reinforcement learning algorithm, the quality update formula, and the intuition behind it. There are three parameters that determine the learning outcomes: scaling factor, future discount factor, and number of iterations. Go ahead and play with the tutorial. Post your questions and feedback. Finally, if you want to name this algorithm, what name will you use? Damn right, this is called Q-learning algorithm. If you understood it well, your journey into other reinforcement learning algorithms will be smooth and easy. Good luck and thank you for watching this video.